Hi and welcome. I'm trying to learn electrical engineering. Today, resistance of a uniform wire, and after we've done it, we're going to do a bit standing yoga. And if you participate in standing yoga, then it's better at your own risk. The resistance of a uniform wire is directly proportional to its length. You should devise a simple experiment to show the truth of this fact. Now, I don't know what a uniform wire is, but I'm going to take it now as a wire. Maybe a specific one, a wire. And we should now make an experiment and prove that it's actually true that the amount of resistance is directly proportional to the length of it. Of course, it follows from our previous work. 2 meters of wire is physically the same thing as 2 identical 1 meter lengths joined in series. And hence the 2 meters will have twice the resistance of each meter of wire considered singly. And hence the 2 meters will have twice the resistance of each meter of wire considered singly. Yes, so if it goes to 1 meter, it has an amount of resistance, and having 2 meters, it is the double amount, or if you're having 2, 1, it will bring it up there. It's directly proportional, okay. Just as the side. I think it is second. It is. Why does it lose proportional and not exponential? Proportional would be able to be exponential, I think. But why does it always lose additional, in the same amount additional? Why does it not get stronger? And why? And the other thing I'm just thinking about is other seismic things of earthquakes. They seem also not to go away quite fast. They seem to go for a long time around the world when an earthquake is, all these things. And I would like to know, but what is that not? Because I think that's not true for echo, but I heard also that loud noise like a volcano explosion is also traveling pretty far and goes consistently down in its noise. Now basically the idea is, are there some things, completely natural things even, which have a different time of going away? That some things are going more faster down, or do all go down in the same way? And what makes the difference with some things, if there's a difference, go away in a direct line, whereas other things go directly down? What is the reason why an earthquake, a seismic wave, can travel on and on and on and just go slowly down, but other things seem to stop faster? A cannonball goes first and one around and down, because the gravity is all the time the same, but at the beginning it moves faster. That's the explanation. Well, just say so the explanation is a cannonball has at the beginning, or any other ball, which has 100 kilometers, and then it goes slower. The gravity pulls it the whole time in 1 second flight time 1 meter down. But in the first second where the cannonball flows, it makes 100 meters. And so it basically does not fall in the first 100 meters. And then suddenly the cannonball has just 50 kilometers left. So it will now fall over the course of just 20 meters down. But now the question is, does now the speed of the cannonball itself go down consistently? Or and this is still electrical engineering, because the would be nice to have a Latin saying the prima questione, whatever. Why does electricity go additional down? And why does it not go, the further it is away, the faster it goes down? What is it making the difference? That it goes differently with different things. Now, consider the 2 identical meter lengths of wire laid side by side with this as 2 resistors in parallel. I didn't understand the part of the parallel resistance. The combined resistance will obviously be half of a separate resistance of each. The combined resistance will obviously be the half of a separate resistance of each. The separate resistance of each. You can check this by imagining each meter to have a resistance of, say, 2 ohms. Then R and I, did I say, was the current. The current divided by the resistance equals 1 divided by 2 plus 1 divided by 2, or 2 divided by 2, because we can keep it together, I think. So R is 1 ohm. But the two wires side by side represents a new wire with a cross-sectional area twice that of the individual wires. The two wires side by side represent a new wire with a cross-sectional area twice that of the individual wire. I don't understand. Putting these two pieces of information together, we can deduce, still the word deduce, use the word deduce, I almost don't know what it means. We can deduce that the resistance of a uniform wire is inversely proportional to the cross-sectional area. What cross-sectional area? And what is now inversely proportional? This again is a result derived from Ohm's law, and therefore the result must be capable of direct experimental verification. Okay, we can prove what we don't understand. To do this, you will need two equal lengths of a wire, which we don't have, of the same material but different thicknesses. Let us suppose you use two single meter lengths of concertan, constant, or contaran. It seems to be a type of wire. One of an 80 SWG and one of a 22 SWG. Concertan is a high resistance alloy containing 60% copper and 40% nickel. Concertan is a high resistance alloy containing 60% copper and 40% nickel. Each piece in turn can be placed into a circuit shown in figure 5. And its resistance calculated as explaining on page 10. Let's go. The diameter of the two wires can be found experimentally by using a metric micrometer. What? The diameter? Okay, the diameter. We can measure the diameter of the 18 SWG and the 22 SWG wire out of constantan, which is 60% copper and nickel, and that is very resistant. We understood that fact, and we're going to do that fact in a moment in this video. The diameter of the two wires can be found experimentally by using a metric micrometer, or finding the values from a table of standard wire gauges as shown. So SWG diameter millimeter 18 has a resistance of 122, 20 0.914, and 22 has 0.711. Okay. This information concerning the resistance of the length of wire can be expressed mathematically. The resistance, I don't know the mathematical symbol, is the length of wire, we're having 2 times 1 meter, and the cross-sectional area of wire. I don't understand what the cross-sectional area of wire is. Or in symbols, resistance is whatever 1 divided by A. The sign, whatever, means is proportional to. So this strange, I don't even know what it is. This strange, whatever, means is proportional to. And you will meet it several times later in the book. Okay, that's the sign of the circle, and the half open circle means is proportional to. Let's go one moment back to the cross-sectional area of wire. But the two wires side by side represent a new wire. Why have a new wire if they're lying side by side? With a cross-section, I don't even know what is a cross-sectional area. I don't understand what it is. So something crosses, and why is it not sectional? Is it the section at which it is crossing, and why does it not make a cross-sectional area? So why is it of the individual wire? Whatever. Now, I understood two things. And that is that this sign mean is proportional to. Now I have a problem. If I make a video, I have to show a sign. If I don't show a sign, it doesn't make sense, particularly because I don't know the name of the sign. I could still say that sign means is proportional to. But first of all, we're going to say that constantan is a high resistance alloy containing 60% copper and 40% nickel. No, let's just do it in the next video. We have just 5 minutes left for yoga and yoga, and I don't want to rush here. And I'm just thinking, what if we say here's something wrong about a concertan wire, where people working with electricity we don't want to say it's wrong. So we want to work out what we actually can say to it, and the other thing to be also later. That means that was for electrical engineering. But if you were here for electrical engineering, you would directly to expert for electrical engineering. We will don't understand you. If you stay and participate in the power yoga, then that's what they honest. Feet are staying together, breathe in the outside. Not the other side. In and up. Out on to the side. In and up. Out to the side. In and up. Inch space between the feet. Out to the side. In and up. Out and down. In and up. Out to the other side. In and up. Out and down. In and up. Lean onto the knees. Breathe in. Out the heel of the back. In into the middle. Out the belly of the back. In into the middle. Out come. Out with the heel. Into the middle. Out the round back. Into the middle. Come with the round back up and make it into the big shoulder. Out. Breathe in as the arms up. Out to the side. In and up. Over the sides down into the chair. Then come halfway up. Come high up and out and up. Breathe in, reach high. Lift out onto the sides. In and up. Over the sides down into the chair. Breathe in halfway up. Higher up and out and coming up. Breathe in up onto tiptoes. Breathe out and sink down. In and up. Out and down. In and up. Out the hands over the sides down. Standing long legs. Breathe in by the right knee. Breathe out, stretch your left leg. In, change. Out, stretch your right leg. In, change. Out, stretch your left. In, change. Out, stretch your right. Into the middle. Out, both legs straight. Breathe in as the right hand up to the sky. Breathe out, bend the left knee, look over the right shoulder to the right hand. Inhale down. Out and down. Breathe in, lift the left hand up. Breathe out, bend the right knee, look over the left shoulder to the left hand. In and down. Out and down. Make hand for space between the feet, just the way to the heels, breathe in and go down. We all come up. In and down. Out and up. In and down. Out and up. Take hold on the elbows and gently rock from side to side. Hands down, feet together. Breathe in, straight back, monkey half lift, halfway up. Out and down. In, halfway up, straight back. Out and down. Breathe in, lift the arms up, hands up. And the hands down. Palms together, elbows together. Breathe in, lift the arms up. Breathe out and down. In and up. Out and down. Hands together, breathe in. Out, stretch in front. Breathe in. Out again in the front. Bring your head up. And back. Feet are sitting together, intertwine the fingers behind the back. Breathe in, tall up, shoulders back. Out, head out to one side. Chin down to the clavicle, a bit slower now. And breathe out, gently reach with the hands down to the ground. Breathe in, lift the gaze. Turn the head out to the other side, shoulders back, tall up, breathe in. Out, chin down to the clavicle. Pull with the hands down to the ground. Breathe in, lift the gaze, back into the middle. And slowly the fingers behind the back, drag over to one side, tall up, shoulders back, breathe in. And slowly concentrate with the head over to the side, with the hands out, chin down to the clavicle. Breathe out, pull the arm and shoulder down. Breathe in, lift the gaze, turn back over to the other side, hands up to the other side, tall up, shoulders back, breathe in. Out, chin down to the clavicle, pull the arm and shoulder down. Breathe in, lift the gaze, back into the middle. Legs are standing around shoulder, without a point of view outside, having an uneven space between the heels, breathe in. And out, chin down to the chest, and roll slowly down. Go down. Bring the elbows against the inside of the knees, breathe in, tall up. And out, tuck the pelvis in and come to the crown of the head first. Up. And down. Now the feet standing together, breathe in, the arms up. Breathe out, lean back, draw the shoulder blades together. Breathe in, lift the arms up. Intertwine the fingers, breathe in, reach, high, screw. Breathe in. Breathe out. Breathe out, reach in front of the back. Breathe in and up. Out, lean back, draw the shoulder blades together. In and up. Over across the arms, intertwine the fingers, reach high. Reflection from left. In and arms up. Out lean back with long arms. In and up. Out and down. In and up. Now hands actually down. Really arms up. Out and down. Again in and up. Out and down. Again in and up. Bring the hands to touch and lower the hands down to heart center. It was with power. I thank you very much and until next time.